Hello and welcome back to BME 2315. In this lecture, we'll be talking about ordinary differential equations. So why do you think we have this picture on the front? Well, it's to give you the idea that differential equations are one way in which computational methods are used to look into the future to see what might happen. So let's first start off by a definition of a differential equation. A differential equation has at least one differential in it, like this, and it has one independent variable. So if you look at this first differential equation, it has a dependent variable, and then it has an independent variable, x. Okay, and if you look at this next differential equation, we see that we have, again, time is the independent variable. Okay, whereas c is the dependent variable. So basically what we're finding is that the dependent variables are the things that are you're predicting into the future, and the independent variables are the things that are being held constant, either by space or time in most cases. Okay. You can also have partial differential equations that are different than ordinary differential equations. Partial differential equations have two or more independent variables. So the independent variables in this partial differential equation are time and space, and then it's also got a dependent variable. You can have one or more dependent variables. As well. So both of the differential equations that we show here on the left are called first order differential equations, in that they have just one derivative in them. But you can also have higher order. This is a second order ODE. Because it has two different derivative terms in them. It has a second order derivative and a first order derivative. But note that this is still a differential equation. It has one independent variable. Sorry, my pen is acting up. One independent variable. And sometimes you might need to rearrange the second order differential equation into and by using a little variable substitution. Basically, if we make a new variable y that is given by the differential in p, and then also that would mean that if you took the derivative of both sides, the derivative of y would be the second order of p. Then you can rewrite this as a system or two coupled first order ordinary differential equations. This is an equivalent first order differential equations. Okay, so that's some basic definitions about differential equations. Now, it's helpful to know that there's a reason why we study differential equations, and the reason is that they get used incredibly often across a variety of different fields. Right? It's used in chemical transport for looking at say transfer of chemicals from one compartment in your body to the next. It's used to model signaling pathways in your body and how certain inflammatory pathways will oscillate in time. It's also used in the laws of motion and in order to look at how molecules initiate the contraction of your muscles and drive force development. So it gets used in quite a lot of examples. Here's an example from my own research where we use a lot of differential equations. Basically, this is a communication network within the cell, and each one of these boxes has a corresponding differential equation to it that allows us to simulate what happens when we add a hormone. Do that. So you added this hormone, and you get widespread communication of that signal throughout the cell, and it compares it to a different one. Okay, and here's another example of differential equations from Natalia Tryanova at Johns Hopkins. She does really cool work to model the heart, electrical activity in the heart. I'm trying to find where. There you go. These are computer models of. Okay, so there's a few different examples of using differential equations in biomedical engineering. And so now let's look at basically how we can start learning how they can be solved. How can we do math on them? So the general form of our differential equations are this form dy dx equals f. And as we said before, there's going to be one independent variable and one or more dependent variables. And so then what is the goal of solving the ODEs? Well, it's for solving for the dependent variables. Okay, which is basically kind of like saying predicting the future. Okay, and all of these Runge-Kutta methods that are going to be used to solve the differential equations are all of the form yi plus 1 equals yi plus some phi times h. Okay, and basically what this is saying is that you use the current state to predict what will happen in the future, given phi, which will show you has information from the equations. So basically, phi provides an estimate of the slope of y over the interval from xi to xi plus 1. So the simplest Runge-Kutta method is called the Euler's method, and you've probably heard of it before. And in that case, phi is just f. It's the right-hand side of the differential equation. So I'll show you a little bit about how that works. If we have a xi xi plus 1, yi plus 1. And the true solution might look something like this. But of course, we're making approximations on that. And so what we're going to do is we're going to be starting out right here at the current value, and we're projecting out we're projecting out and kind of guessing that that was the right point. And so that, of course, has some error associated with it. Right? Yeah, and that the slope that we're using was f of xy. Okay, so basically we're just like using it the current slope and project out and assume it's a straight line for a while, and get to this point, and then there's going to be some error associated with that. And also let me make additional note that this is the step size, the difference between xi and xi plus 1. Okay, so let's look at how we could actually, so this is just like a schematic of what this looks like, and this will look like this in general. But let's now look at it for a real problem. We're solving a differential equation dy dx equals x over y, and we're going to solve it using Euler's method. Okay, and so what that means by Euler's method is that yi plus 1 equals yi plus f of xi yi times the step size right here. And then also, of course, that xi plus 1 equals xi plus h. Okay, and in this problem, that is our f of xy. Okay, so we're going to start by looking at our initial conditions, and we say the initial condition is that at x equals -2 and 3. So we say x equals -2 and 3 right here, and on this plot right here, that's at this point right here. Okay, and then we compute the f. F is x over y, and so that's -2 over 3. Okay, and then yi plus 1 is this -2 over 3 times, okay, let me write out the whole thing. It's 3 plus -2/3 times 1 equals 2 1/3. Okay, and then that value gets placed down here for the next time step. Well, let me actually I can update our plot. Is that at x -1, it's around here. Okay. Okay, and then so we're going to update our time. It's going to be -1 at the next step, and then yi is 2.33, and then you take the ratio of these, and you get -0.4 286. Okay, and then if you take the yi is 2.33 plus this slope times 1, you get 1.905. Okay. And then finally, on the next step, we're at 0 and 1.905. Always gets carried over from the last one. And 0 over 1.0905 is 0. And what that means is that we're going to have the same y value at the end. Okay, so that basically showed us that we could go from a differential equation and stepping through it one at a time using Euler's method. So let's now talk about the error involved in computing these solutions, because there definitely is error that as occurs. So on this plot right here, this initial line is showing what happens with the analytical solution, and then this other line, this lower line, shows what would happen if you compute Euler's method one time after another. And one of the main takeaways is that not only is there error, but the error gradually increases the more steps that you take. And so because of that, we find that the local truncation error is on the order of h squared, but the global truncation error is on the order of h. Okay, so basically you get a larger, as h goes down, basically you get a larger global error from multiple iterations than you do from a single step. And as h goes down, truncation error goes down. So remember, this is just like what we were talking about in Taylor's series earlier in the class, is that the smaller steps that you take, the smaller the error is going to be. So it's a good idea to be slow and careful when you're computing these differential equations. Oh, and then you're right. So this is a nice little animation showing what happens with a step size of 1, a step size of 0.5, or a step size of 0.1, and you get closer and closer to the analytical solution with that. Okay, so far we just talked about how to solve for one differential equation, and it's the same idea for calculating for more than one. The basic idea is that now, so this is it's said in a very compact form, where y are now, these are now matrices, and you can see that's the same form. But let me write out what that looks like to you. So you've got a dy1. Actually, we're going to go with x dependent. Okay, so you had something like this. Okay, then you can put this in a matrix form. And actually be the same form even if you had a lot of additional terms. And so this is the same function term. I should have put a 1 and 2 on these. Okay, but this is just to show you that you can cast on these equations in a matrix form, and that's what you'll actually be doing and solving on one of your homework problems. Okay, so this is almost as a break just to show you some really cool things can happen in this differential equation. So this is the Lorenz attractor, and this is famous. It was originally a weather model, but it's probably most famous for just the beauty of what this Lorenz attractor, this figure 8 pattern, and it shows how sometimes very unpredictable it can be. And so there's a lot of mathematicians around trying to understand it, kind of its underlying properties. Here I'll show you a little video of. Oops. Let me see a little video. It's really cool looking. It's just amazing to me that such complex behaviors can be explained by just 3 differential equations. Okay, so that's one example of a system of differential equations. We're going to use a little bit simpler one to do for our hand example. To kind of walk you through the process. So first off, we're going to start at ti equals 0. And from our initial conditions, that tells us the starting values. So it's 1 and 2. And then these are our f values right here. So our f values are going to be the first one is just going to be 1 times 2. Which is 2. And the other one is going to be 3 times t of 0, which is 0, minus y1. So 3 times 0 minus y1 is 1. So you get minus 1. And then to compute our y, our next y, we're going to do 1 over 2 plus 2 over minus 1. Remember that the 1, 2 is our initial y, and then this is our slope that gets multiplied by our step size, 0.5. And so that gives you 2 and 1.5. Okay? So that's one step. And so now we can take another step. So our step size is 0.5, right? And we're starting off at 2 and 1.5 from the last step. And then this is going to be 2 times 1.5 because we're just multiplying the things together. And we got 3 times 0.5 minus 2 from the second differential equation, 3 negative 0.5. And if you put those together, you get 3.5 and 1.25. Alright, so that just kind of shows you how you can pretty logically walk through these differential equations over time. Alright, so the key points for today's lecture is that differential equations can be used to model many different biological processes. Euler's method is kind of the foundation of a series of methods called Runge-Kutta methods, and they all approximate the solution using the slope at a current location. Other methods that we'll look at use additional information, and error depends on the step size. So the smaller step that you can take, the better the answers will be. And one of the things that's nice about the Euler's method is it extends directly to a system of different differential equations. So you can look at many different parts working together as a system rather than just a single equation. So I hope that was helpful for you, and I hope to see you soon.